Now, what do we do if a population standard deviation, sigma, is unknown? Two things. First, we substitute the sample standard deviation, denoted by S, for sigma. This gives us an alternative to the standard error of a mean. Hat sigma sub x bar is equal to S over the square root of n, instead of sigma over the square root of n. Second, instead of using the normal distribution, we assume that the sampling distribution of a mean follows the student's t-distribution. For a large sample size, these distributions are very close to one another, but for a smaller sample size, the difference is more significant, which is relevant because in this case, the sampling distribution of a mean is not normally distributed anyway, unless the original population is. The t-distribution has a parameter known as the degrees of freedom, which in this case is the sample size minus 1. Instead of finding z sub alpha over 2, we find a value t sub alpha over 2 n minus 1, such that the probability that capital T sub n minus 1, the random variable for the t-distribution of n minus 1 degrees of freedom, is greater than this value is equal to alpha over 2. As with a normal distribution, we can find this value using table lookup. Then, this is what we multiply by our alternative standard error of a mean to get the margin of error, capital E. Then we have our confidence interval. To illustrate this modified procedure, we revisit our example of a signal transmitted 10 times, but now the variance is unknown. We use the sample standard deviation to find the standard error. Since the sample size is 10, the number of degrees of freedom is 9. So, we use a t-distribution table with probability 0.025 and 9 degrees of freedom to obtain this value. Then we multiply that by the standard error to obtain our margin of error, which then gives us our confidence interval. Now that we know how to construct confidence intervals for the mean, it is essential to interpret them properly. It is a common misconception that if we have a 90% confidence interval obtained from a single sample, then there is a 90% probability that the true population mean falls within this interval, but that is not the case. Rather, what we know is that there's a 90% probability that any given confidence interval we obtain from a sample will contain the population mean. In other words, a confidence interval based on a single sample doesn't tell us very much, but if we have confidence intervals obtained from several samples, then we get a clearer picture. Here we have 10 confidence intervals. They all have the same radius, which is a margin of error capital E, but different centers, which are the sample means x bar. Because the confidence level is 90% of the confidence intervals generated from several samples will contain the population mean, as in this plot, where one of the 10 confidence intervals misses the population mean completely. There are some parameters that affect the confidence interval. First, we consider the effect of the confidence level. As it increases, the significance level alpha decreases. It follows that the area under the normal distribution curve that is outside the confidence interval shrinks, so the value z sub alpha over 2, or t sub alpha over 2 n minus 1, increases. In other words, the confidence interval widens. And it becomes less likely that the population mean is outside the confidence interval. Another parameter is the sample size n. As it increases, the margin of error decreases, which then causes a margin of error to decrease. Therefore, the confidence interval shrinks, which is to be expected because the larger our sample size, the more accurately the sample mean should reflect the population mean. Now we shift gears and consider confidence intervals for a proportion. Technically, the proportion follows a binomial distribution, but if a sample size is large enough, this is well approximated by a normal distribution, so we make that assumption here. To construct our confidence interval, we use the standard error of a proportion, except that we use a sample proportion p sub s in place of a population proportion p, which is unknown. Then we compute z sub alpha over 2 in exactly the same way as for confidence intervals for the mean. Its definition is the same. Then our margin of error is obtained in an analogous manner as for the mean, z sub alpha over 2 times the appropriate standard error. Then we have a radius of our confidence interval, and its center is a sample proportion, just as it was the sample mean before. We conclude this section with an example. We poll 600 voters and obtain a sample proportion of 52%. We want to find a 95% confidence interval for a population proportion. We use the sample proportion and sample size to obtain the standard error of a proportion, and then obtain z sub alpha over 2 from a normal distribution table. Multiplying this value by the standard error, we obtain the margin of error for the confidence interval, which turns out to be 4%. We can use a given margin of error to obtain an appropriate sample size, just as we did for the mean. We rearrange a formula for the margin of error to solve for n, which gives us this formula here. However, if p is unknown and we don't have an estimate for p prior to taking a sample, we can just use p equals 0.5, because that value of p maximizes the value of the expression p times 1 minus p, thus giving us a conservative estimate of a necessary sample size.